completeness requires an axiom system. Let's go to economics. I have 3 examples in economics. One which I picked in that book by Vela, Computer Economics, 2001, isn't it?
And then he has 2. One is in 2000 and one in 2010.
Yeah. A discussion we had a few years ago, which was supposed to give a paper. I hope we can still write a paper.
Yes, the paper that we had planned.
Yeah, the paper that was.
Thank you very much.
No, you're most welcome. Because I have been thinking about it for a long time, and we have lots of interesting queries in it. And second, the theorem which was suggested by my student, my PhD student, Marcelo Tsuji, he's a Brazilian economist, and which derives from a theorem by Elaine Lewis, who is also a fascinating character. Result by Vela. Basically, I picked up this result. These comments originally appeared in the Jabil paper. It was published some 5 years ago, I think. And essentially, I tried to give an example in something related to economics, specifically in picking up not a result which I had formulated myself, but which came from someone from the field of economics. That's why I chose Vela's example. And to show the relation between undecidability and incompleteness.
May I just comment on proposition 1.1? Just briefly.
Please.
Because I think I know a little bit of the background. This proposition that you're going to talk about, there is a paper by Lucas, which is one of the fathers of rational expectations, that he published an article about the fact that the rational expectations decisions can be the process of adaptive learning. So you have that the agents are learning with adaptive ways, and then it converges towards the rational expectation decisions. So this proves that there is no algorithm to decide whether the decisions are rational expectations, basically. That's the equivalent. It's the important. It's one of the examples where it is important. So the rational expectations are really not important.
Yeah, I was supposed to give all these details, but I try to compress
Of course.
as much as possible. So, thank you very much.
No, sorry if I interrupted. But
No, I'm grateful to you for giving this background. Vela's result is derived from a classical result in computer science, which is the unsolvability of the halting problem. And Vela's result is there is no algorithm to decide whether a given class of decision rules is a steady state of some adaptive process, which is a kernel of Lucas' contention. Well, we can see the relation between both results. This is, I'm not mentioning any axiomatic background. This can be done in what we call informal mathematics without having resort to axioms. Now I require an axiomatic background. If S is consistent, I'm going to give all the details now. It has a model with standard arithmetic for its arithmetic portion. For some alpha, a class of decision rules, the sentence, now this is a formal sentence, alpha is a steady state of an adaptive process, is such that neither it nor its negation can be proved within S axiomatic framework. Okay, it looks a bit weird. Let me explain. First of all these theories can be formulated in a reasonable way within set theory, within fragments, portions of set theory. We use a technique called, I mentioned Pet-Supis. It's called the Supis predicate technique, which allows us more or less to formulate axiomatic theories for most portions of sciences which use mathematics as its main tool, ordinary kind of mathematics. So we can formulate the theory of adaptive processes and the like within set theory. And this is the meaning of theory S. The technical condition has a model with standard arithmetic, means that there is an interpretation for this axiomatic theory where numbers are numbers. This seems trivial, but it's not trivial, because I'm going to tell you about non-standard interpretations, which these results have, whose meaning, whose economical meaning, I have no idea of what they could be, and which nevertheless are a consequence of these results. We have to deal with them. I'm going to suggest a few approaches. So, Veda's very clear statement becomes something more convoluted because we have to deal with an axiomatic framework and the like. But this means that within this axiomatic framework, we can explicitly write a set alpha, which we can interpret as being a set of adaptive rules, such as the sentence, which appears between quotation marks, is not derivable, nor its negation is derivable from the axioms of the system. Okay. So incompleteness exists in economics. Now it's a discussion Stefano and I had a few years ago. Stefano showed me Mirowski's paper on the interpretation of economic actors as finite automata. What are finite automata? They are restricted computers with very rigid behavior rules. And the suggestion Mirowski makes is to avoid undecidability and incompleteness, suppose that we consider the actors in an economic setting as being just finite automata. Since everything is finite, his contention is, we would be able to decide everything. Undecidability and, of course, incompleteness would vanish. Can we do that? No, we can't. I told him on the spot when he... unfortunately, of course, if you list a given set of finite automata, you may prove that they are just finite automata. But you may have this situation. If S is consistent, then the sentence F cursive is a family of finite automata is a sentence independent of S. This means I can give you an explicit family. It's more or less sketched in the remark before the proposition. I can give you explicitly write a series of programs which will be in the world of ordinary numbers. They will be finite automata, programs for finite automata, you can check that, but which cannot be proved to be a family of finite automata within our theory. This is something very strange and results from the fact that we use a function f with no serifs over there, which is a computable function, which is total. Total means has no bugs, is defined for every value. But you cannot prove that within your axiomatic framework. These functions are very interesting, they appear everywhere, and they are related to a very weird-looking function which can be characterized in a very simple way called the busy beaver function, which appears in lots of mathematical problems and which is such that no computer program can compute it because it grows too fast, grows beyond everything which is computable. These are a kind of local busy beaver functions, the way we see a busy beaver function from within an axiomatic theory. We are learning lots of weird things about axiom systems, which seem to be something so intuitive, and yet there are lots of pitfalls inside them. The third example is the Tsuji theorem. I owe Marcel Tsuji for that theorem. We presented it in a 1998 paper, which is published, that big book which Stefan just showed you. And let me tell you how Tsuji told me about its proof. He was one of our graduate students at that time in São Paulo, and he was very respectful. Yes, and may I talk to you, Professor Doria? Yes, please do. We sat for 5 minutes at the cafe of the philosophy department, which houses a large group in São Paulo, and he explained to me, use that technique you developed to prove a stronger version. I'm going to say why it's stronger. A stronger version of Alain Lewis' result on the undecidability and incompleteness of games. It leads, obviously, to the fact that you cannot have, even if you have stable prices for competitive markets, as is guaranteed by the Arago theorem in macroeconomics. In the general case, you cannot compute these stable prices. And I know that you are right. It was a 5-minute talk which led to this paper, which is really my own. I just gave the tools. The idea was Marcel's, my most interesting contribution to economics. I'm very proud of it, by the way.
Oh, of course, this is a very important result. But economists would have an axiom saying, let's assume that we are in equilibrium, that the system is in equilibrium.
Okay.
Without computing it, so that's what we have is equilibrium. That is what
it's an ad hoc procedure.
Yeah, of course.
This is one of the versions of the Tsuji result. Equilibrium, there is a competitive market, and so there's a sentence. The set P of prices for M is a set of equilibrium prices is undecidable with respect to the axiomatization we can give to the theory of competitive markets. There are several axiomatic treatments. One of them was also given at our group in São Paulo. I believe it was published somewhere, someplace, some mathematical economics journal, and also I gave an axiomatic treatment. I myself gave an axiomatic treatment to game theory, which appears in several papers of mine, including the Tsuji paper. Now, okay, these are examples in economics. Now we have the problem of dealing with interpretation, because this is what really attracts me in this question. I have been thinking about it for the last years and have no idea of which could be the way out of this conundrum. Physics has a very blunt way of dealing with unpleasant situations. It uses what is called a super selection rule, which gives, okay, let's exclude these solutions because they are, quotation marks, unphysical. Let me give you an example which comes from general relativity. The Einstein equation, what we call the Einstein equation, the equation of the gravitational field, and they allow you to describe sets of universes, models for the universe. And some of these, actually the huge majority of these universes have time coordinates with a very weird behavior. You have time machines, you have a time which is local but not global, this kind of statement which appears everywhere. The universe was created, exploded, appeared some 14 billion years ago, doesn't have any meaning within most physical theory, most models for the universe derived from the Einstein equations. So, which was Stephen Hawking's solution?